Welcome back to my YouTube channel. Today I'm talking about type 1 and type 2 error. Okay, so when we're doing hypothesis tests, there's two different errors we can make. So for this, I'm going to use the example of a two-sample t-test. So we're just comparing two group means. The null hypothesis would of course be that they're the same. The group mean, the population mean of group 1 equals the population mean of group 2. The null, so that's the null hypothesis. The alternative hypothesis is that they're different in some way. And it could be less than, it could be greater than. It really doesn't matter, because this is a two-way test, so it's not different in some way. So there's two ways we can be wrong. We can say group 1 and group 2 are different when they're not. That's a type 1 error. We're saying an effect exists when it doesn't. So we test the null hypothesis in this hypothetical situation, but the groups are not different in reality at the population level. And the probability of type 1 error is alpha, which is frequently 0.05. So in the t-test example, we set alpha to 0.05. We found an effect when an effect didn't really exist, and the probability of that was that 0.05. So type 2 error, denoted as beta, is the probability of when the probability of failing to detect an effect that really exists. So, in that example, the population means are different in some way, and we fail to detect the null hypothesis. So then, there was an effect, we failed to find it. It could be related to power. Maybe we didn't have a large enough sample size to find that effect. Maybe there wasn't a large enough effect size. Maybe the true difference in population means is 0.0001, and we needed many more subjects to find that effect. Okay, so I have a brief comparison on my website. So type 1 error. We test the null hypothesis when it is true. False positive. I found a difference, but there was no difference. Many times we start to care more about type 1 error. That's not always true, but type 1 error is a big deal. You don't want to say things have an effect when they don't. So type 2 error, you fail to find an effect when it exists. So yeah, you miss an effect that really exists. Some people may argue that it's almost never the case that there isn't an effect. If a scientist does an intervention, there's probably some effect. And I might get canceled for saying that, but it probably is. But it is so great that we would ever notice or care about it. It's unclear. If it's not big enough to notice the effect, maybe we don't care about it. And now we're getting into ideas of effect size and power, but some might say that, yeah, you're always going to have some effect. It's just whether or not it will actually matter enough to be found or really intervene in some way that the scientists or public cares about. Okay, so let's talk about how you reduce errors. Increase sample size. That works for both. Type 1 and type 2 errors both do better with increased sample size. It is never wrong to do that. Set an appropriate alpha level. Note, this acts like you have a huge choice in that. 0.05 is probably what you're going to use. You can go more strict, but I would not go less strict. You can go 0.01 if you want, but so if you do that, what you're doing is, yeah, you're setting the probability of a type 1 error lower. So then there's only a 1% chance of that. But for you as the person doing the test, you are more likely to not find an effect, not be able to publish your work, and have a bad time when you could have just used 0.05. Unless you're in a specific field that really necessitates 0.01. You can conduct a power analysis with, yes, in theory you can. You use effect size and the statistical design, the experimental design, to estimate the sample size you would need to get a specific effect. I've always thought that this kind of moves the thing you need to guess at to a different place. So before you do the power analysis, you have to guess at n. When you do the power analysis, you have to guess at effect size. Either way you're guessing, it's the way you're guessing. And I guess the conclusion is that people would rather guess at effect size than n. And perhaps that's decent. If you have like a justification for why you don't care about effect size is lower than a certain amount. But this thing, conduct a power analysis, doesn't solve all problems. And use replication also is kind of a good in practice idea, but practically, are you going to do the same experiment twice? Absolutely, that's a fantastic idea. Do you have enough money and time to do that? No idea. I don't know who you are. So, replication is fantastic, and we should invest a heck of a lot more into replication. But practically, we don't reward replication like we ought to. Okay, so that's the end of the video. Thank you for watching.